Okay, Assalamualaikum and very good morning. Okay, so today we are going to continue with another type of antenna, which is the reflector antenna. So the figure shows some example of reflector antenna, and the common types of reflector antenna used is the parabolic dish or parabolic antenna, as we can see in TV satellite communication, the astro dish, and then the radio communication station, for example the Gun Healy, known as the UK gateway to space, where it stores very large or huge parabolic reflector antennas for radio communication purposes. So what is the reflector antenna? So the geometry includes passive or parasitic element and also active elements, where the active elements is where the antenna is fed, okay, the feeder point, while the passive or the parasitic element is the dish itself or the parabolic itself. Right, so the reflector antenna consists of a reflective surface. So this is the reflective surface in which it is used to collect or project energy such as light, radio waves, and sound. And the parabolic reflector transforms all incoming waves along the axis into spherical wave converging towards the focus. So the waves from the feeder will be traveling in spherical motion. Okay, when it reaches to the reflector surface, so the waves will be reflected back. So here then it will be reflected back, and it will produce collimate waves, in which a race of waves travels in parallel to each other. So all the waves are in phase, therefore the concentration is higher. So the concentration is higher, hence the reflector antenna is used for higher directivity applications. Alright, so since it is highly directional and it's suitable for long distance communication, and it works at high frequencies above megahertz frequency bands. Okay, this slide shows different types of reflector. So we have the plane reflector. However, so this is the feeder, the feed point, and this is the reflector, a flat surface. So however, this plane reflector produce quite scattered waves, so the concentration is, or the directivity is minimal. And another types of reflector is the curved front end or Cassegrain feed, where a parabolic type of reflector is used, in which the waves from the feeder will be traveling in spherical motion or spherical configuration, so until it reach the reflector surface, and the waves will be reflected back in phase. So these are the collimate waves. Okay, so it has a higher directivity if compared to the plane reflector. Right, there's another one. So this is called parabolic reflector, and another one is the corner reflector. Okay, where the plane is cornered, okay, that's angle of 90 degree if it is used, a plane surface is used, and if the bended surface is used, so the signal will be again traveling from the source. This is the source, so it's traveling in a spherical motion, so it will be reflected back from the surface. Okay, same goes to this configuration, but the directivity is better than pre-reflector, but it's lower than the parabolic types of reflector. We are going to focus on the common types of reflector, which is the parabolic reflector. So as mentioned earlier, so all the waves originating from the feed, okay, from the antenna, will be reflected back, and the waves are in phase. Okay, so the waves are in phase, the collimated waves in phase. So since all waves are in phase, so the radiation is strong and the concentration is higher, so the signal will be directed towards the intended direction effectively, right? So for this kind of antenna, we can see that the radiation pattern will look something like this, very high directivity towards this direction, but it has narrow beam width, okay, and very little or minor side lobe and back lobe. Right, so the advantages of the parabolic reflector, okay, it has minor lobes, side lobes and also back lobes, so it can reduce power usage, okay, since the all energy is directed towards the intended direction. Equivalent focal length, feed can be replaced at any location, so we can control the feed point or feed position, and we can adjust the beam, okay, so we can direct towards the intended direction. But the disadvantage of this parabolic reflector, okay, some of the power gets reflected from the parabolic reflector due to the obstruction, and this usually occurred when the dimension of the paraboloid is small. Okay, example of application of parabolic reflector are the Cassegrain feed parabolic for satellite communication and a wireless communication system as well. Okay, let's look at the geometry of parabolic reflector. So you have the reflector surface, parabolic reflector here. Okay, and you have the feeder. Okay, you have an antenna being fed here. Okay, so the components are, first you have the focus. This is the focus point where all incoming waves are concentrated, and then the signal will be propagating in a spherical motion towards the surface of the reflector, where the vertex is the innermost point of the reflector, and it is centered on the parabolic structure. Right, so the distance between the focus point here to the vertex is known as focal length. So F represents the focal length, where it represents the distance between the focus point to the vertex. Okay, and the Z0 is the distance from the focal point, the focus, to the edge of the rim. So the edge of the rim here. Okay, to this point, so it is Z0. Okay, and then the angle between the center to the edge of the parabolic structure is known as theta naught. It is the subtended angle. So the subtended angle can be determined by using this equation where it depends on d. So what is d? So d is here is the diameter of the parabolic structure, and this area, this opening, okay, from here to here, this opening is known as aperture, okay, where it is described by its diameter. So the diameter of the opening or the aperture of the parabolic structure. Okay, alright, so the two important parameters to in parabolic reflector design is the theta, the subtended angle. This is the subtended. Okay, and z naught, the distance from the focal point to edge, and also the ratio between the focal length to the diameter of the parabolic or the aperture. Okay, so the relation between the theta, the subtended angle, and also the focal length is known as F over D ratio. Okay, and usually its values is from 0.25 to 0.5. So this is normal range of F to D ratio. Okay, next, what is illumination? So illuminates basically lights up the intended area. So when you have a point source at the focus point, for example here, so the energy from that focus point will be radiated towards the reflector. So this is the reflector, just like a bulb that lights up a room. So the energy radiated not in the intended direction will be wasted, and it is expected that there's additional loss due to the reduction of the radiated power as the power will be reduced with the square of the distance. Therefore, less energy is expected at the edge of the structure if compared to the center. Alright, so the loss is commonly called space attenuation or space taper. Alright, so the blue color here representing the illumination loss is the space attenuation, and also the spillover loss in this region outside the intended beam width. Alright, so in order to improve this, we need to adjust the feed pattern so that the constant illumination can be achieved. Alright, so the energy missing at the edge here, as mentioned earlier, is the illumination loss, while the energy misses the reflector. Okay, so it outside the beam width. Right, so it is spillover loss. Right, this is how it looks when it has a uniform feed illumination and also uniform reflector illumination. Okay, next we are going to look at the important parameters in designing a parabolic reflector antenna, or the important parameter to evaluate the performance of the parabolic reflector antenna. Right, the two main factors that contribute to the aperture efficiency is the spillover and also non-uniform amplitude distribution losses or illumination losses. And the losses dependent primarily on the feed pattern. So as mentioned in the previous slide, we can adjust the feed pattern in order to minimize the losses. Okay, so if we can control the feed pattern, so we can also compromise or control the spillover and also taper efficiency. And in practice, maximum refractor efficiencies are in the range of 65% to 80%. Right, we can calculate the gain of the parabolic antenna by using this equation, in which the AE is the aperture dimension. Alright, so the aperture of parabolic reflector, and then so the D is diameter of the reflector. Okay, and then epsilon AP is the efficiency of the aperture efficiency. Alright, so aperture efficiency dependent or is the product between the other efficiency such as the spillover efficiency, taper efficiency, phase efficiency, polarization, blockage, and random efficiency. Right, so and the beam width from the irradiated pattern can be calculated by 70 lambda divided by D. Again, D is diameter of the parabolic structure. And the directivity of the antenna is given by this equation, pi d squared. D is the diameter and lambda is the wavelength of the resonance frequency. Okay, so this equation basically represents the D naught max. Okay, the maximum directivity of the parabolic structure. So multiplied by the one in the bracket here. Okay, the one in the bracket here representing the epsilon AP. Alright, the aperture efficiency of the antenna. Right, and the aperture efficiency for n equal to 2 is given by this equation, where it dependent on the subtended angle. Okay, so the subtended angle theta naught can be calculated by using the equation from earlier slides. Alright, so if the antenna is 100% having the 100% efficiency, therefore epsilon AP equal to 1, or otherwise the system will state the efficiency of the system dependent on the other efficiencies, as for example the spillover, the taper, and etc. Now let's look at an example on parabolic reflector antenna design. So a 10 diameter reflector with an F to D ratio of 0.5 is operating at frequency of 3 GHz. The spillover and taper efficiencies given as 80% and 90% respectively. Calculate the following. Right, first the antenna aperture efficiency, overall antenna directivity and gain, and lastly the power received if power density 100 milliwatt per meter squared is used. Alright, so as usual, before we begin, refer to the suitable and correct equations. So the first one is the antenna aperture efficiency given as epsilon AP. Okay, efficiency epsilon AP, and the equation is basically the product of the following efficiencies: ES, ET, EP, EX, EB, and ER. Right. So ES is spillover, T taper, P for phase, X polarization, B blocking, R random. Right, so but in the question only 2 efficiencies given, and these are the 2 most factors that affects the parabolic reflector efficiencies. Therefore, we just need to consider both the epsilon S and epsilon T. Right, so in this case, it is equal to epsilon S multiplied with epsilon T, which is equal to 80% is 0.8 multiplied with 90% is 0.9. So then the epsilon AP equal to 0.72. Okay, next, question 2, overall antenna directivity and gain. Okay, number 2, directivity is G0. Again, refer to the equation. So it is basically the multiplication between DO max, the maximum directivity multiplied by the aperture efficiency. Right, so it is pi d over lambda squared multiplied with the aperture efficiency. Right, in this case, D is the diameter, so it's given as 10 meter, and then the lambda is not yet calculated, so let's calculate the lambda equal to C over F equal to 3 times 10 to the power of 8. The frequency given is 3 gigahertz, so it's 3 gig, so the lambda is 0.1 meter. So now you can calculate your D naught equal to, so pi, your D is 10, pi squared, your D is 10 divided by 0.1, the lambda, don't forget to square them, and then epsilon AP from the previous calculation, 0.72. So your D naught is equal to 71061.512 dimensionless, and in dB it is equal to 10 log of your D naught is 48.516 dB. And one more is the gain. Okay, from the, I think the second chapter on the antenna parameter. So fundamentals and parameters. So the PR, so the gain, I mean the power received. Okay, the power received PR, we have seen this in the first 2 chapters, okay, in the fundamentals of antenna design. So for the gain, okay, as shown in previous slide, so the gain equal to 4 pi AE, the aperture size, EAP, this is the aperture efficiency divided by lambda squared. So in this case, we still don't have the AE. So from previous slides, the AE, the aperture size is equal to pi d over 2 squared. So d is the diameter. So pi 10 over 2 squared. So AE is equal to 25 pi. Okay, so your G is equal to 4 pi over lambda. Lambda is 0.1 squared multiply with EE 25 pi multiply with epsilon AP 0.72. So your G is equal to 71061.512, and in dB it is again 48.516 dB. Okay, and lastly, number 3, power received So PR is equal to the efficiency of the receive, or in this case it is the one that we have is the aperture efficiency multiplied with dr. This is a general equation, so the directivity of the received signal. So in this case we only have one antenna, so it is the same as d naught, and then lambda squared over 4 pi multiply with the power density. Alright, so epsilon r is the EAP 0.72, and dr is your directivity is 71061.512 multiply with lambda squared 0.1 squared divided by 4 pi, and the power density given is 100 milli. Okay, 100 times 10 to the power of minus 3, so your PR is equal to 4.07 watt. Okay, with that, thank you.